Chapter 7, Periodic Trends. Periodicity is the repetitive pattern of properties for elements based on atomic number. So we're going to see here different properties that will increase or decrease as we cross the periodic table across like period or in a group. So periods are the horizontal lines of the periodic table. So group 1, periods, period 1, period 2. Periods, horizontal lines. Groups, vertical, the columns, right? We here. Groups, vertical, periods, horizontal, right? So here. The first property is nuclear charge. Nuclear charge, the total charge of the nucleus in an atom. And to calculate here, the effective nuclear charge is atomic number, Z, minus S, screening constant. And the screening constant is usually a number that is usually closer to the number of inner electrons. So, for example here, carbon and nitrogen, right? Carbon has atomic number 6, here, Z6. And nitrogen has atomic number 7. And here, the Z for nitrogen is 7. Okay. And then S, the screening constant. So as you know that the screening constant is usually a number closer to the inner electrons, right? So let's use the core electrons, right? First here. Carbon 6 electrons, so let's write the electronic configuration here. 1s2, 2s2, 2p2. So 6 electrons here, right? So all the electrons that they are in the highest energy level are the outermost electrons, or also called valence electrons. And everything that's not in the highest valence here, the highest energy level, will be the core electrons, or also called inner electrons. So here, in carbon, you have only 2 core electrons here, right? And so let's do a subtraction. Carbon 6, atomic number minus 2, so 4. So the effective nuclear charge for carbon is a number closer to 4, around 4. And nitrogen has atomic number 7. Let's write here the electronic configuration. 1s2, 2s2, 4, 2p3, 7, right? So the highest energy level here is the number 2. So all the electrons, they are in the highest energy level here, are the outermost electrons, or valence electrons. But for this, to solve this math here, you need the number of core electrons. So everything, all the electrons, they are not in the highest energy level, will be the inner electrons. In that case here, nitrogen is 7 atomic number minus 2 for the inner electrons here. So the effective nuclear charge for nitrogen is 5. Okay, so now let's talk about period trend. Period horizontal lines, right? Periodic table here. So the effective nuclear charge increases from left to right across a period here. So it's increasing this direction, as we saw here, right? Carbon, we calculated here, was 4, and nitrogen was 5, so increases from left to right. Because the protons number increases and the number of core electrons remains about the same. And you saw that the read, right? Both was still 2 core electrons. And so the effective nuclear charge increases from left to right, also because the valence electrons are pulled more tightly to the nucleus here. Right? Okay. So now let's talk about group trend. So group trend, right? Groups are the columns, so the vertical here, right? So the effective nuclear charge in the group trend remains about the same going down in a group here. So ground in a group here, the effective nuclear charge remains about the same. So why? Because the numbers of protons increases, okay, you know, right? Go increases here, so as you go down here, the numbers of protons increases, but the number of electrons also increases. So the effective nuclear charge remains about the same. Here, okay, so let's use an example here using sodium, and potassium, right here. Sodium atomic number is 11. Okay, so atomic number is 11. Let's write 11 here, minus the inner electrons. So for sodium, the highest energy level will be, everything gonna be the number 3. And all the others electrons here will be the 4 electrons or inner electrons, right? How many electrons you have here? 2 plus 2, 4 plus 6, 10. So sodium is, the effective nuclear charge for sodium is 11 minus 10, so just 1. Okay, and then here, down in this group here, you have potassium, right? Potassium, the atomic number for potassium is 19. So 19. The electron configuration for 19. So 1s2, 2s2, 2p6, 10, plus 3s2, 3p6, 18, plus 4s1, 19. Right, so you saw atomic number 4. So here's the effective nuclear charge mass here. Atomic number 19 minus inner electrons, right? So which one has which energy level is the highest energy levels here? So we're going to choose the highest number. So here, energy level 1, 2, 3, and 4. So this 4 here, the highest energy level. So all the other electrons that are not in the highest energy level will be the inner electrons, right? So how many inner electrons you have here? 2 plus 2, 6, 10, plus 2, 12, plus 6, 18. So 19 minus 18, 1. Actually, here they have the same number, right? So the effective nuclear charge for sodium is 1. And potassium is also 1. So this is why for the group trend, the effective nuclear charge remains about the same. Because as the protons increases, the electrons also increase, so will not change. Now let's go to another property here. Sorry, let's wait to get one. Okay, the next property here is atomic size. The radii here is the half of distance between nuclei in a bond. So we have, for example, here two atoms, right, bonded one to another here. And the distance between the two nuclei here will be this size that we are talking about here. So the period trend, right, that's from the horizontal line. In the period trend period, the atomic size decreases from left to right because the numbers of electrons about the same, but the protons increases. So here, the protons, right, they are in the nucleus here. So the number of protons are increasing. So the nucleus, the electrons, they getting closer to the nucleus. If we're getting closer to the nucleus, the atomic size decreases here. So the electrons will get closer to the nucleus. It's like this. Protons are positive, right? And the electrons are negative. This is why it's like they have the attraction. And as the numbers of protons increases, the electrons, that's still about the same, will get closer here. This is why if you compare here, so for example, compare carbon with nitrogen. So in this direction here from left to right, the atomic size is blurry. Okay, better. Decreases, so the nitrogen is smaller than carbon. Okay. The next is about group trend. So the atomic size when you in a group trend, right? Group trend are the vertical columns, right? The columns. So when you go increases, the atomic size increases when you going down in a group because the numbers of electrons increases, causing the valence electrons to be further from the nucleus. So here, the electrons are increasing, right? So yes, in that case here, the atom, it's increasing. In another example here, the electrons were about the same. The protons were increasing, but not the electrons, about the same. That's why in down in a group here, the atomic size increases. Right? Okay. The next is ionization energy. Ionization energy is the minimum energy required to remove an electron from the ground state of a gaseous atom or ion. Okay, here. So the ionization energy increases from left to right in periodic table because the effective nuclear charge also increases. So the effective nuclear charge will be like a shielding here, right? Between the nucleus and the electrons. So if the nuclear charge will be higher, you need more energy to remove the electrons, right? And also here you know they're gonna be smaller, the size, right? So gonna be harder to remove these electrons. This is why you need more energy. This is why here, the energy to ionize the gases here will increases from left to right. Okay. And then the group trend, like, so when you go up here, the ionization energy going up in a group here increases because the valence electrons, this V here means valence. Valence electrons means the outermost shell, right? Are held together, are held more tightly by the nucleus due to a smaller atomic size. So here, right, the atomic size increases from top to bottom. That means if we look like bottom to top, the atomic size of the atoms will decrease. So if the atoms are smaller, so they're gonna be held more tightly. So gonna be harder to remove the electron. That means we're gonna need more energy to remove this electron going up here. All right. Like it's easier to remove this electron than these electrons here. Right. Larger the atom, you need less energy. So it's gonna be easier to remove the electrons. Smaller the atom, higher will be the energy needed here. All right. So, okay. Next topic is about ionic size. Right. So you saw everything related to size, right, is the opposite of the other one. So the other ones, when you go from left to right, increases, right? But for size, when you go from left to right, everything about size will decrease here. The period trend, atomic size, the ionic size decreases from left to right across a period. The reason here is the same reason for the atomic size, right? Because you have the same numbers of electrons, but the protons increasing. If increasing here, you have more attraction, so the atoms get smaller here. But here talking about cations and anions here. So the cations are smaller than their parent. The cations are smaller than the parent atoms. For example, okay, so sodium has 11 electrons, right? And sodium plus the cation, right? Cations are the positive ones, the one that lost electrons. So if they lost electrons here, the cations, they will be smaller because you have less electrons. So in the anions are the ones are larger than the parent atoms. So for example, fluorine, right? So when you have F minus here, right, the fluoride ion, they have the anions, they have one extra electron, right? They have like more electrons. And the charge will be negative because it has extra electrons. So the anions are larger than the parent atom. So cations are smaller than parent atoms, and because they have less electrons, the numbers of protons is the same, right? Because sodium ion, they have 11 protons above, right? So here they have the same number of protons. But the sodium plus has only 10 electrons, and sodium 11 has 11 electrons. Right, the same thing, actually the opposite direction will be the anions. Anions are larger than the parent atoms because anion has more electrons. For example, fluorine, right, the atomic number is 9. So the both, they have the same atomic number. So number of protons, 9 protons, but this fluoride here has 10 electrons, and the fluorine here has only 9 electrons. So more electrons. If you compare speeds of the semi-atomic number, the one that has more electron will be larger, right? Okay. Okay, so and in a group trend here, you saw that the ionic size, when you go down in a group, right? We saw that the size increases, right? So it's the same thing. Atomic size, everything about size, when you go down in the group, will be the whole one that is going to be increased will be related to the size. Metallic character too, but in that case here, talking about the size. So everything related to the size will be the ones that are going to be decreased when you go down in a group. By the same reason here, right? Because the numbers of electron increases, causing the valence electron should be further from the nucleus. So the same reason here. Okay, so size of ions. So when we have isoelectronic series here, in an isoelectronic series, ions have the same number of electrons, right? Okay, iso means the same, right? Iso, the prefix iso means same. And the ionic size decreases with increase in nuclear charge. For example, here, isoelectronic series of 10 electrons. I'm going to see here that 10 electrons, right? O2 minus, F minus, sodium ion here, right? Plus magnesium 2 plus, aluminum 3 plus. All these ions here, they have 10 electrons, right? But what to change here? So they are different elements. So if they are different elements, they have a different number of protons. So oxygen 8, fluorine 9, sodium 11, magnesium 12, and aluminum 13, right? Okay, so you can see here, when the atomic number increases, the size decreases, are seen here. The size is decreasing here, right? Because when you have more protons, let me show here, right? With the size, when the proton increases, right? Protons increases here, the electrons outside will get closer to the nucleus. If it gets closer to the nucleus, the size will be smaller, right? Okay. Okay, and then the next property here is about electron affinity. Electron affinity is the energy change in the addition of an electron for a gaseous atom, right? So period trend, right? That's the horizontal line here. The electron affinity increases from left to right on the period. Because when the nuclear charge increases, you have more affinity. The electron affinity also increases. So you have more attraction by the electrons are here. In a group trend, so group trend is what is about the vertical, right? The columns here. So in the group train, electroaffinity decrease when going down in a group here because the added electrons is further from the nucleus, right? And they experience like weaker attraction due to increasing the size. So that means they have weaker attractions, gets weaker as the size gets larger. Atomic size increases. So the attraction gets weaker when the atom increases here. Right. And then the last properties is about electronegativity. Electronegativity is the tendency of an atom in a molecule to attract shared pair of electrons. So, period, right? That is the horizontal line here. The electronegativity increases from left to right across a period because the effective nuclear charge increases. So the valence electrons that get closer to the nucleus make the atom more likely to attract electrons. Right here. So the electronegativity increase from left to right. And in a group trend, right, that's the vertical one, the electronegativity when going down here decreases going down in a group, right? Because as the atomic size increases, the valence electrons are further from the nucleus, so be reducing the atom's ability to attract electrons. All right. Okay, so yeah, chapter 7 is very short. The shortest chapter is just about periodic table properties. All right. Okay.